You know that feeling, right? You're trying to get your head around something complex, maybe prepping for work, or just keeping up with a field you care about.
Oh, definitely. Information overload is real.
You want to be informed, but honestly, who has time to wade through everything? It can feel, yeah, overwhelming.
Finding those key insights quickly, that's the challenge.
Absolutely.
Uh,
And, well, that's why we do this. Welcome to the deep dive. Think of us as your shortcut to understanding. We do the digging, pull out what matters, basically for you.
and today we're diving into something pretty exciting at the edge of AI. Specifically, how we can help AI get much, much better at planning complex tasks.
Right. The mission today is looking at this thing called InstructRAG, and a really interesting idea tied to it, the instruction graph.
Yeah, and this isn't just theory. We're talking about tech that could make AI agents genuinely more helpful in the real world.
Like what? Give me some examples.
Well, imagine AI that can tackle really complex questions, or navigate virtual spaces, even help you shop online more effectively.
Okay, practical stuff.
And the really cool part, I think, is how it learns. It's not just programmed rules. It actually looks at past successes
Uh-huh.
and uses that knowledge, that history, to figure out new problems. There's a kind of aha moment when you see how it connects successful past steps.
Interesting. So where are we getting our info for this deep dive?
We've got the main research paper. It's titled InstructRAG, Leveraging Retrieval-Augmented Generation on Instruction Graphs for LLM-Based Task Planning.
Okay.
And also another source that goes into a bit more detail specifically on the instruction graph concept itself.
Great. So let's jump in. Why is task planning actually hard for AI? Especially these large language models, or LLMs. They seem pretty smart.
That's really the starting point, isn't it? LLMs are, they're incredibly capable. They seem like natural fits for being intelligent agents that can plan.
Because they understand language, can generate text.
Exactly. And people are using them for more and more complex tasks.
What kinds of tasks are we really talking about here, beyond just answering questions?
Well, think about multi-hop reasoning, where you need to connect several pieces of information.
Okay.
Or embodied tasks like an AI controlling a robot in a virtual house to find something.
Right, like actually doing things in an environment.
Yeah. Or web shopping, searching, comparing, deciding, even scientific reasoning, maybe forming a hypothesis based on data. All multi-step processes.
Gotcha. Those definitely sound more involved than just a simple query. And isn't there a common way these LLM agents work? Something like thought, action, observation.
Exactly. The TAO cycle. The agent sort of plans the next step, then it takes an action like clicking the button or running a search.
Then
Then it gets an observation, what happened, what's the result, and that feeds back into the next thought. It's a loop.
okay, that cycle makes sense. So where's the weak spot? What limits them in planning these complex tasks?
Well, the big one, according to the research, is knowledge limitations. They're trained on huge data sets, sure, but they don't necessarily know the specifics of every possible complex task or the best way to go about it.
So they might not know the perfect sequence of actions, or even what actions are possible for a specific goal.
Precisely. Their internal knowledge might just not cover it well enough.
Okay. So how do we help them? How do we give them more knowledge for planning?
And that brings us neatly to RAG, retrieval-augmented generation.
ARGAD. Right. We've talked about that concept before. Quick refresher for anyone new in this task planning context.
Sure. RAG basically lets the LLM pull in information from outside databases or knowledge sources while it's planning.
So it's not just stuck with what it was trained on months ago.
Exactly. It can retrieve relevant, timely information on the fly.
Like if I ask about a movie director, it could check IMDb right then and there using ARGAD.
That's the idea. It grounds the LLM's planning and actions in external, potentially more current or specific information, which, should lead to better plans.
Sounds powerful. But the paper we're looking at mentions two specific hurdles when using RAG for task planning. Enlargeability and transferability. What are those about?
Yeah, these are really key challenges the researchers pinpointed. Enlargeability. That's about dealing with questions or tasks that are sort of within the AI's general knowledge area, but maybe not in the exact form it's seen before.
Oh, so?
Okay, imagine it knows how to look up a country's capital, and it also knows how to look up its population, but maybe it's never been asked to find both for the same country in one go.
Ah, so can it combine those known skills to answer the new, slightly different request?
Exactly. Can it enlarge its capabilities beyond the explicit examples it was trained on? That's enlargeability. It needs that flexibility. Like having Lego bricks, can it build something new from the pieces it has?
Okay, that makes sense. And the second one, transferability.
Transferability is about adapting to totally new kinds of tasks, things outside its original training domain.
Right. So if it's great at answering factual questions, how quickly can it learn to, say, navigate that virtual house we mentioned? That feels like a different skill set.
Completely different. That ability to transfer knowledge and adapt quickly is crucial if we want these agents to be truly versatile.
So enlargeability for variations within a domain, transferability for jumping to new domains.
Yeah.
Big challenges. How does InstructRAG try to solve them?
Okay, so InstructRAG. This is the novel approach proposed in the paper. It's designed specifically to hit those two challenges, enlargeability and transferability.
And how does it work? What's the core idea?
At its heart, it uses a framework called multi-agent meta-reinforcement learning.
Whoa, okay. Let's unpack that. Multi-agent suggests more than one AI working together.
Correct. And meta-reinforcement learning. Well, meta-learning means it's learning how to learn, essentially, how to adapt faster to new tasks.
Okay, learning to learn. And multiple agents involved. What are the main parts?
There are three core components working together. First, and probably most central, is the instruction graph.
Right, that was in the title.
Second, an RL agent, that's reinforcement learning agent. And third, an ML agent, the meta-learning agent.
Okay, instruction graph, RL agent, ML agent. Let's start with the graph. What is an instruction graph?
Think of it like a map, but a map of successful strategies. Formally, it's a directed graph, so nodes connected by arrows showing a flow.
Okay.
And this graph organizes successful instruction paths from the past. Basically, sequences of actions that work to solve previous tasks.
So it's a structured memory of what worked before. What are the nodes and the edges, the connections representing?
Good question. The nodes, often labeled V, in graph theory, they represent instruction sets. Think of them as clusters of similar individual actions.
Similar actions.
For example, one node might group together actions like search movie title, search director name, search actor name, all search actions, just slightly different targets.
Okay.
Another node might have lookup release date and lookup genre, different kinds of lookup actions.
So nodes group similar types of steps. What about the edges connecting them, labeled E?
The edges represent task sets. They essentially record the kinds of tasks or specific questions that were solved by following the path connecting those nodes.
Ah, so an edge might show that going from a search node to a lookup node is common for answering when was X released kind of questions.
Precisely. The edges capture the relationship between action types in the context of specific tasks.
Makes sense.
Yeah.
How do they build this graph? It needs data, right?
Absolutely. It uses what they call a support set, basically. Training examples where they already know the question, the right answer, and a sequence of actions that successfully gets that answer.
So known good examples. What's step one?
Step one is generating those successful instruction paths for every question in the support set. You figure out the sequence of actions needed for each example.
Okay, so now you have a collection of successful recipes, essentially. Step two, how do they get into the graph structure?
This is where it gets interesting. You take the individual instructions from those successful paths and insert them into the graph. But it's not just sticking them in anywhere. They use a similarity threshold, let's call it delta, and a technique called approximate k-nearest neighbors search, or AKNN.
AKNN. Sounds like it's finding similar things.
Exactly. When adding a new instruction, AKNN looks for the most similar instructions already in the graph. But crucially,
Yes.
it specifically avoids comparing it to the instruction that came immediately before or after it in its original successful path.
Why is that? Why ignore the neighbors from the original sequence?
Because the goal is to group instructions by function, not just because they happen to appear next to each other once. You want nodes to represent general capabilities like searching for a person or looking up a date, not just one specific sequence.
Okay, that's a clever distinction. So AKNN finds similar but not immediately adjacent instructions. Then the threshold, delta.
Right. If the similarity found by AKNN is below the threshold, delta, meaning it's not very similar to anything already in the graph, excluding those neighbors, it creates a new node for this instruction.
A new category of action, essentially.
Sort of. But if the similarity is above the threshold, meaning it's quite similar to an instruction in an existing node, then the new instruction is added into that existing node. It gets clustered with its similar counterparts.
And the edge information, the tasks.
When an instruction gets added to an existing node, the task information, what question was this path solving, gets recorded on the edge leading into that node from the previous step in the path. So edges collect data on the task context.
Wow, okay. So it builds this network dynamically based on similarity and past success. What's the big payoff for the listener trying to grasp this? Why structure it this way?
Two main benefits jump out. First, it's just a really neat way to organize successful strategies. You can almost visualize common pathways for solving certain types of problems.
Right, I can see that.
But the second and maybe more powerful benefit is that it directly enables enlargeability.
Back to challenge number 1. How does the graph help with that?
Because nodes group similar instructions, they act like junctions or connection points. The system can potentially create new paths by combining segments from different past successful paths.
So it can mix and match steps from different historical solutions.
Exactly. Even if it hasn't seen the exact sequence ABC before, if it has paths like ABD and XBC and B represents a similar type of action in both, it might be able to figure out ABC is a valid path for a new problem.
Can you give a quick example?
Sure. Let's say one node has lookup capital city from answering what's the capital of France, and another, maybe closely related or even the same node, has lookup population from population of Germany.
Okay.
Now a new question. What's the capital and population of Italy? The system might navigate a path using a search instruction, then grabbing lookup capital city from the node, and also grabbing lookup population from the same or a connected node, even if that specific combination wasn't in the original training data. The node acted as that junction.
That really clears it up. The graph provides the flexibility to assemble new solutions from known good parts. Okay, so that's the graph. What about the two agents, RL and ML? What are their jobs?
Right, the agents, the RL agent, the reinforcement learning one, its main role is exploration. It navigates the instruction graph.
Navigates how?
It tries to find promising sequences of instructions, potential paths through the graph that might solve a new query, one from the query set used for testing. Think of it like a scout checking out different routes on the map.
So it proposes potential solutions based on the graph's structure.
Pretty much. It explores the possibilities laid out in the graph.
Okay, then what does the ML agent, the meta learning agent, do?
The ML agent then looks at the paths suggested by the RL agent and selects the most relevant or promising one for the specific query at hand.
It chooses the best route proposed by the scout.
Kind of, yeah. And once it picks a path, it uses that sequence of instructions to guide the main LLM in generating the final response.
It provides the chosen path to the LLM.
Exactly. And this is where it really tackles the second challenge, transferability.
How does selecting a path help the system adapt to totally new types of tasks?
The meta-learning aspect comes in here. By learning to select the best path based on just a few examples of a new task type, the ML agent helps the LLM quickly grasp the kind of strategy needed. The selected path acts almost like a template or a strong hint provided to the LLM within its prompt.
Like saying, for this new kind of problem, strategies that look like this have worked before.
You got it. It's providing a relevant, structured example derived from past experience, tailored by the ML agent's selection process.
So the ML agent learns to pick good templates for new situations.
That's a good way to put it. And these agents work together. The RL agent explores, the ML agent selects, the LLM executes, and then the outcome success or failure feeds back as a reward signal.
To train the agents.
Exactly. It helps the RL agent find better paths and the ML agent make better selections over time. It's a meta-reinforcement learning loop optimizing the whole planning process.
That sounds like a really sophisticated system. The graph providing structured memory, the RL agent exploring it, and the ML agent selecting and adapting. Does it actually work better?
Yep.
What did the experiments show?
Well, they tested it quite rigorously on 4 well-known benchmark datasets.
Which ones?
Hotpot QA, that's for multi-step question answering. ALF World, that involves simulated agents doing tasks in virtual environments.
The embodied tasks.
Right. Then Web Shop simulating online shopping tasks. And Science World focusing on scientific reasoning problems. So, a real mix.
Okay, good spread. How did InstructRAG do against other methods? The existing state-of-the-art.
The results were pretty impressive. On unseen tasks across all these datasets, InstructRAG significantly outperformed the established methods. They mentioned names like React, Reflection, RAP.
And significantly means?
Well, for example, on Hotpot QA, they reported improvements of up to 19.2% over the strongest baseline. That's quite a leap.
Wow, nearly 20% better on one benchmark. Was it consistent?
Yes, the paper reports consistent gains across all 4 datasets, suggesting it's not just good at one specific thing, but generalizes well to different complex planning scenarios.
That hits the enlargeability point.
Right.
What about transferability? Did they test adapting to completely new datasets?
They did. For instance, they trained it on Hotpot QA, question answering, and then tested it directly on Science World, scientific reasoning without specific retraining for it.
Yeah.
And it still outperformed the baselines, showing strong cross-dataset transfer. It could take what it learned about planning in one domain and apply it effectively in a quite different one.
That really does speak to transferability.
Yeah.
What about noisy data? Does the graph need perfect past examples?
That's a practical point. They actually tested its robustness by intentionally adding incorrect or noisy past paths into the instruction graph.
How did it cope?
It showed pretty good resilience. Performance degraded, as you'd expect, but not drastically, suggesting the agents can learn to navigate around or ignore some of the bad information in the graph.
That's important for real-world use. Did they also check if all the parts were necessary? Like what if you took out the graph or one of the agents?
Yep, they did an ablation study, systematically removing each key component, the graph, the RL agent, the ML agent, to see the impact.
And the verdict?
The results confirm that all three parts are crucial. Take away the graph, performance drops. Take away the RL agent's exploration, it drops. Take away the ML agent's selection and guidance, it also drops significantly. They all contribute meaningfully.
Okay, so we've gone deep into the mechanics. Let's pull back up. For our listeners, why does this matter? What's the big picture takeaway?
I think the key thing is that this represents a really solid step towards AI agents that are more reliable and, crucially, more adaptable for complex real-world stuff.
So beyond just lab benchmarks.
Yeah. If you care about getting information efficiently, this shows how AI is learning to learn from experience in a smart, structured way. It's moving towards tools that could genuinely help us handle complexity better.
What kind of future applications could stem from this if it keeps developing?
You could imagine, down the line, much smarter virtual assistants, right? Ones that can handle really complex, multi-part requests without getting confused.
Okay.
Better tools for researchers, maybe, that can synthesize information more effectively. Even more capable robots in logistics, manufacturing, perhaps eventually even homes.
It all comes back to that idea of learning from structured past success, doesn't it?
It really does. That combination of the instruction graph as a memory and the agents learning to use it, that seems to be the core insight here that leads to these performance gains. It's quite an elegant approach.
Absolutely. It's that aha moment. Structure meets learning.
Right. So InstructRAG, with its graph and its two agents learning together, it really does offer a promising way forward for AI planning, learning from the past, adapting to the new.
So, wrapping up our deep dive today, InstructRAG uses this clever instruction graph, a map of past successful actions, plus an RL agent to explore it, and an ML agent to select the best path and adapt, tackling those key challenges of enlargeability and transferability in AI task planning.
And hopefully this discussion gave you, our listeners, a good shortcut to understanding what's happening at this research frontier.
Definitely. Now here's a final thought to maybe chew on. How could this core idea, building a structured memory of success, and then using intelligent ways to explore and adapt from it, apply elsewhere?
That's a great question. Could you apply similar principles to, say, personal learning? Or how organizations tackle new complex projects, learning from what worked structurally?
Something to think about. The implications of more capable, adaptable AI are vast. And if you are interested in the nitty-gritty, the research paper is out there.
Indeed. Lots to explore.
Well, that concludes this deep dive. Thanks for joining us, and we'll be back next time to explore another fascinating topic.